Welcome to the course on error control coding and introduction to convolutional codes. In this lecture today, we are going to talk about classification of convolutional codes based on type of connections between the output and the input. Also based on what are our output bits, we will classify convolutional codes into systematic and non-systematic codes. Then we are going to talk about how we can realize convolutional code using shift registers. So, as I said, first we will talk about convolutional codes, and in this we are going to talk about a classification based on types of connections between the input and output of the convolutional encoder. In this regard, we are going to talk about what do we mean by feed forward encoder and feedback encoder. Then we are going to introduce a classification based on what are the output bits, whether the information bits directly appears in the output or not. Based on that, there will be a classification of convolutional code. The encoder basically where information bits can be separated out is known as systematic encoder, and in non-systematic encoder we cannot separate out information bits directly from the parity bit. So, we will talk about what do we mean by systematic encoder for a convolutional code and a non-systematic encoder, and then we will introduce this concept of equivalent encoders. So, for every non-systematic encoder there is an equivalent systematic encoder, and through an example we are going to illustrate how we can get its equivalent encoder. Then we are going to talk about a class of encoder where if the input bits are very high weight, we can still get an output code word of very low weight, and these kinds of encoders are known as catastrophic encoders. And finally, we are going to talk about two different types of realization of convolutional codes using shift register. The first one, which is known as controller canonical form realization, and the second one is known as observer canonical form realization. And finally, we are going to conclude this lecture with the concept of minimal encoder. So, let us start our discussion on classification of convolutional encoder. The first type of encoder that we are going to talk about is known as feed forward encoder. So, what is a feed forward encoder? The encoder corresponding to a polynomial generator matrix which does not have any feedback from the output to the input is known as feed forward encoder. Let us take this example. This is our information sequence. VD denotes our coded sequence. What is the generator matrix G of D? In this case, it is given by 1 plus D. Note here, the generator matrix here is a polynomial generator matrix, right, as opposed to a rational generator matrix, and there is no feedback from the output to the input side. You can see basically the output depends on the current input as well as the input one past time instance. So, there is no feedback from the output to the encoder side, and this is an example of a feed forward encoder. Now, we can represent the output of a feed forward encoder as linear combination of current input and finite number of past inputs. We also refer this type of encoder as non-recursive encoder, and as we said, in this we have an example of a rate 1 code, because input 1 bit, output is 1 bit coming out, and the generator matrix of this rate 1 code is given by 1 plus D, and you can see this is an example of a feed forward encoder whose generator matrix is a polynomial generator matrix, and there is no feedback from the output to the input side. And this is its corresponding state diagram for this feed forward encoder. This is another example of a feed forward encoder. We can write down the generator matrix for this G of D. V0 is nothing but the input bit, so this first one is just 1. And what about the second parity bit? This is information bit, so we have 1 plus one delayed version of this information bit plus D cube, because this is 1, 2, 3, 3 time instance delayed version of U. So, this is a generator matrix. This is also a polynomial generator matrix, and there you can see there is no feedback from the output to the input side. Now, let us look at what do we mean by feedback encoder. As opposed to a feed forward encoder, the encoder for a feedback encoder has a rational generator matrix. Please note, here we had a polynomial generator matrix. For a feed forward encoder, we had a polynomial generator matrix, whereas for a feedback encoder, we have a rational generator matrix with at least one non-polynomial transfer function containing a feedback path from the output to the input. Look at this example. From the output, we can see there is a feedback going to the input side, and the generator matrix for this is basically, so first coded bit is nothing but the information bit, so that is 1, and this is basically 1, 1 plus D. So, because there is a feedback from the output to the input side, the output of a feedback encoder can be written as a combination of past input as well as past outputs. Hence, the output depends on infinite number of past input, because the current output depends also on past output, and past outputs also depends on past inputs and past outputs. So, the output will basically depend on infinite number of past inputs. Now, feedback encoder is also known as recursive encoder, and we just now mentioned one example of this feedback encoder is given in this figure. This is a rate 1/2 code. You can see for one input we have two outputs, and its generator matrix is given by this. This is its corresponding state diagram for this feedback encoder. This is another example of a feedback encoder. So, there is one input and there are three outputs. We can write down the generator matrix G D. The first output is nothing but the information bits, so that is 1. Now, what are the feed forward terms in V1? So, V1 depends on this bit and this bit. So, this is 1 plus D square, and what is the denominator term? We have basically 1 plus D plus D square term. Similarly, V2 is basically given by 1 plus D, and this is 1 plus D plus D square. So, this is a generator matrix for this feedback encoder. The next classification that we are going to talk about is based on output bits, whether we can separate out the information bits from the coded bits. So, in a systematic encoder, a rate k by n systematic encoder, the k information bits appear unchanged in the output. So, out of those n coded bits, you can directly see the k information bits, and rest n minus k bits are your parity bits. And the generator matrix corresponding to a systematic encoder is known as systematic generator matrix. Take example of this rate 1/2 feedback encoder. You can see there is one input and there are two outputs. So, it is rate 1/2 and it is a feedback encoder. There is a feedback from the output to the input side. You can see here the first coded bit is nothing but the information bit, and the second coded bit is parity bit basically coming out from this convolutional encoder. So, from these two coded bits we can easily find out what the information bit was from this bit. So, we can separate out the information bit from the coded bit, and this is example of a systematic encoder. As opposed to a systematic encoder, in a non-systematic encoder, we cannot separate out the k information bits from the n coded bits. This is an example of a, one second, I want to make it a rate 1. This is actually rate, just a typo, this is a rate 1 code, because there is one input and there is one output. This is a rate 1 and this is a feed forward encoder. You can see there is no feedback from the output to the input side. So, it is a rate 1 feed forward encoder, and you can see the output bit is given by this current input bit and this past input bit. So, you cannot directly take out the information bits from this coded bit. So, this is an example of a non-systematic encoder. We could also define a class which is called partially systematic encoder. So, in a partially systematic encoder, so if you have a rate k by n partially systematic encoder, out of those k information bits, some of them appear unchanged in the output, while some of the information bits do not appear unchanged in the coded bits. So, in a systematic rate k by n encoder, we can see directly the k information bits. In a partially systematic encoder, we can see a fraction of these k information bits, maybe few bits like from 1 to k minus 1, and in a non-systematic encoder we cannot see any systematic bit in any information bit directly in the output. So, all the parity bits are essentially linear combinations of current and past inputs and outputs. Now, that brings us to our next topic of discussion, which is the concept of equivalent encoders. So, before we define what is an equivalent encoder, we will define what do we mean by equivalent generator matrix. So, we two convolutional generator matrix, let us call it GD and G prime D, are equivalent if they encode the same code. Now, what do we mean by encode the same code? So, the set of code words generated by this and this, if they are same, then these generator matrix are equivalent. Now, the set of code words generated by these generator matrix are same, but the mapping between the input and the output is different in this encoder from what the mapping between inputs and output is for this generator matrix. Now, we say two convolutional encoders are equivalent if their generator matrix are also equivalent. In other words, if their generator matrix encode the same code, then we say two convolutional encoders are equivalent. So, if GD and G prime D are equivalent, this condition should hold. So, two generator matrices are equivalent if and only if there exists a rational invertible matrix T of D such that we can obtain G dash D by TD multiplied by GD. Okay. And we can see basically, so let us say set of code words generated by G dash D. So, that would be VD, it will be UD times G dash D. Now, this we can write as UD TD times G of D, and let us call UD TD as U dash D GD. Okay. So, let us take an example. This GD 1 plus 1 by 1 plus D and G dash D, which is 1 plus D 1, these are equivalent encoders, because we can write G dash of D as 1 plus D times G of D. Okay. So, and we can see this is a systematic encoder, generator matrix for a systematic encoder. Okay. Now, for and this is a feedback encoder, this is a feed forward encoder. So, let us take an example of a non-systematic feed forward encoder, and let us try to find its equivalent systematic encoder. So, what would be the equivalent systematic encoder corresponding to this non-systematic encoder? The generator matrix G dash of D should be of the form identity and some matrix P. So, what we want is basically we want this to be of the form 1 0 something here, 0 1 something here. So, we want to convert this into a form of this type. Okay. So, we will do elementary row operation to bring this generator matrix into a generator matrix of this form. So, first, so we will do this transformation, row 1, we will try to make this as 1. How can we make this as 1? If we multiply row 1 by 1 plus D, if we do that, this term will become 1, this term will become D by 1 by D, and this term will become 1. We leave the second row unchanged. Next, we want to get a 0 here, right. How do we get a 0 here? We do this transformation, row 2 will make it row 2 plus D times row 1. So, the first row is unchanged, but second row we do this transformation, it is row 2 plus D times row 1. So, row 2 here is D plus D times row 1, which is another D. So, D plus D is 0. Similarly, row 2, this 1 plus D square by 1 plus D, this is basically given by this, and we have 1 plus D which is this term. So, what we have done is, we have converted this into form 1 0. Next, we want to get a 1 here, right? We want to get a 1 here. So, how can we get a 1 here? We will do this following transformation. So, for row 2, we will multiply row 2 by 1 plus d divided by 1 plus d square. So, if we do that, then this will become 1. So, we leave the first row unchanged. Here 0 if we multiply by this, it does not change. If we multiply this by this, we get a 1 here, and here we get this term. So, now what we have got so far is, we got a 1 here, we got a 0 here, got a 1 here. Now, what else is remaining? We have to make this a identity matrix. So, we have to make this as 0. How can we make this as 0? We multiply this by this and add it up to the first row, we can make it a 0. So, next to row 1, we add d times 1 plus d times row 2. If we do that, the modified generator matrix that we get is this. Note now, this is a generator matrix for a systematic encoder. You have your identity matrix here, and you have some matrix here, which is your P matrix. So, this is basically the generator matrix for a systematic encoder. So, note now, by simple row operations, we were able to get an equivalent systematic generator matrix for a non-systematic encoder whose generator matrix is given by this. Next, we will explain the concept of catastrophic encoder. So, a convolutional encoder is catastrophic if it encodes some information sequence which has large weight, which has large number of ones, into a code sequence with finite number of ones. So, if you have an information sequence, let us say u of d, which is 1, 1 plus d. Now, this is a sequence of all ones. This is basically nothing but 1 plus d square, So, this is a sequence of all ones. Now, if you have an encoder which maps a sequence, input sequence which has large number of ones into a sequence, coded sequence with finite number of ones, now that type of encoder is known as catastrophic encoder. Now, why is it catastrophic? So, to illustrate it, we will take an example. It is a catastrophic encoder because a finite number of channel errors can result in infinite number of input errors, because you have your information sequence which has large number of ones, possibly infinite number of ones. Because that information sequence is getting mapped to a coded sequence with finite number of ones, if error happens in those locations where you have finite numbers of ones, then your output sequence will get transformed into an all 0 sequence, and your decoder will think that you have transmitted an all 0 sequence, whereas actually you had transmitted a sequence of all ones. So, finite number of channel errors in case of a catastrophic encoder can result in infinite number of input errors. Let us take an example of this encoder with generator matrix GD, which is given by 1 plus d and 1 plus d square, and let us feed input which is all sequence of all ones, which I can write as 1 by 1 plus d. Now, if this information sequence passes through this encoder, what would be your output sequence? Your output sequence would be 1, and this will be 1 plus d. So, what you will get is, you will get an output sequence which has weight only 3, whereas your information sequence has infinite number of ones. So, here is an example where an input sequence of very large number of ones getting mapped to an output sequence of only weight 3. What if error happens in these 3 locations where you had ones? Then your output sequence that the decoder will receiver will receive will be all 0 sequence, and the receiver will think that you transmitted all 0 sequence, whereas the input is all 1 sequence. So, you can see in case of a catastrophic encoder, a finite number of errors. In this example, only 3 errors can result in infinite number of errors, input errors. Okay. This I have explained. Next, I am going to come to the topic of realization of a convolutional encoder. How can we represent a convolutional encoder using shift register? So, given a generator matrix, how can you implement a convolutional encoder? So, in this we are going to talk about 2 such type of realization. The first one that we are going to discuss now is known as controller canonical form realization. So, in a controller canonical form realization, if you have a rate k by n convolutional encoder, we use k shift registers. So, the number of shift registers used is equal to number of information sequence that you have, and the output is obtained by using n set of adders, 1 for each output sequence. And in this case, the k input sequence enter the shift register from the left hand side, and we take the output from the right hand side. The next point to remember here is, in case of a controller canonical form realization, these n adders that are used to obtain the output sequence, the coded sequence, these adders are external to the shift registers. So, they are not inside the shift registers. So, let us take an example of a rate 1 non-systematic convolutional encoder whose generator matrix is given by this. So, in the numerator you have f0 plus f1d plus f2d square, like that. Similarly, denominator you have 1 plus q1d plus q2d square, like that. So, how can we implement this using controller canonical form realization? So, let us go back. So, we are going to use k shift register. So, this is a rate 1, 1 by 1. So, there will be only 1 shift register. So, we use one set of shift register corresponding to 1 input sequence. Next, we use n set of adders. Now, what is n here? Because it is a rate 1, so n is also 1. So, we will use one set of adders, and these set of adders, basically this output that we are seeing, we have this n set of adders that we are using to obtain this coded sequence V. Now, the k input sequence enter the shift register from the left hand side. So, we can see here the input is entering from this hand side. So, since this is a feedback encoder, so let us first look at the numerator term. What do we have here? We have f0 plus f1d plus f squared d. So, this input is basically multiplied by f0. So, the current input is getting multiplied by f0, then one delayed version of the input is getting multiplied by f1, 2 delayed version is multiplied by f2. So, you can see this is then f0, this is f1, this is f2, and again whether there is a connection from this input to the output, depending on that f0, f1, f2 will be either 1 or 0. If there is a connection, this will be 1, if there is no connection, this will be 0. So, you can see this is f0, this is f1d, f2d square, like that. Basically, if this is mth delay element, this will be Fm dm. Similarly, you go back and look at the denominator. We have 1 plus q1d plus q2d square, like that. So, this is the input 1, this is the d term u1 d term. So, this is multiplied by q1, this is d square term multiplied by q2, like that, and then finally you have dm term which is getting multiplied by qm. So, you can see this is how we can realize a convolutional code using controller canonical form realization. Please note, these adders are external to the shift register, there is no adders here internal to shift registers. The inputs are entering on the left hand side, whereas output is taken from right hand side. Now, contrast this with observer canonical form realization. So, in observer canonical form realization, we need to realize a rate k by n encoder, we require n shift registers. Now, please note, for the controller canonical form realization, we required k set of shift registers, whereas in this case we require n set of shift registers, one for each of the coded bits. The second difference is the k input sequences in the observer canonical form realization, these k sequences enter into the shift register and these adders are internal to the shift register. If you recall, in case of a controller canonical form realization, the input is entering here, and at each time instance when your clock comes, they shift to one location to the right, this will move to here, this will move to here. Whereas, in the observer canonical form realization, these inputs are directly entering into the shift register and these adders are internal to the shift register. We will give an example to illustrate what we mean. The lowest degree term generator matrix represent the connection to the right hand side of the shift register. In case of controller canonical form realization, the lowest degree term was on the left hand side. Here the lowest degree term will be on the right hand side. So, let us take the same example that we considered earlier. So, we are considering the same generator matrix and we are going to realize this generator matrix now using observer canonical form realization. So, again here k is 1, n is 1. So, we have n is 1. So, we have one set of shift registers. So, this is one set of shift registers. Next, what did we say? The k input sequence entered the adder internal to the shift register. And what do we mean by internal? So, these are the shift register elements, delay elements, and note these adders are in between the shift registers. These adders are internal to the shift registers. Okay. And next thing that we said was the lowest degree term in the generator matrix represents connection to the right hand side. You see here, the inputs are directly coming to the adder. So, this term is corresponding to f0 u of d. This term corresponds to f1 d of u of d. Whereas, in the controller canonical form, the leftmost term was f0 and the rightmost was fm. Here it is just opposite. So, you can see this is f0 term, f1 term, f2 term, and similarly in the denominator you can see this is q1, this is q2, like that this will be qm. Same generator matrix can be realized using two different forms. So, let us take an example to illustrate this. So, we are considering a rate 2 by 3 systematic feed forward encoder whose generator matrix is given by this. Now, let us try to realize this generator matrix using controller canonical form realization and observer form realization. So, the parity check matrix for this is given by this expression. We will just show you that. So, in controller canonical form realization, we have, so there are two inputs here. So, we will have one set of shift register for each of the input. So, we will have one set of shift register for this and one set of shift register for this. And to realize this, we need two memory elements, because here the highest degree of D is 2, and to realize this we require one memory element. So, total we will require 3 memory element. So, that is what I said, for the controller canonical realization for this rate 2/3, this is my n, this is k, and this is the memory order. We basically require 3 memory elements to represent this convolutional encoder in the controller canonical form realization. Now, what about observer canonical form realization? In observer canonical form realization, we use one set of shift register for each of the n coded bits. So, how many coded bits we have? We have 3. One is this, one is this, and one is this. Now, how many memory elements you require to represent this? 0. This is directly the input coming in here. Here 0, because the direct input is coming here. And what about this? Its maximum degree is 2, so we will require 2. So, overall for this generator matrix, if we try to realize it using observer canonical form realization, we require only 2 memory elements. And in the next slide, I am going to show you those 2 encoder realization. So, let me just write down the generator matrix. So, my generator matrix G of D is 1 0 0 1, then what do we have? 1 plus D square, 1 plus D square, 1 plus D. So, one set of shift register for this. So, this maximum degree is of this is 2. So, we use 2 memory elements, and for this maximum degree of D is 1. So, we use 1 memory element. Okay. Now, what is the first output? First output is directly input U1. So, this is my U1. Second output is directly U2. This is basically this. And the third output is 1 plus D square of U1. So, this is U, this is the D of U1D, and this is D square of U1D, plus 1 plus D times U2D. So, 1 plus D meaning one term is U2 and second is delayed version of U2. So, this will be my third coded bit. So, you can see, to realize this generator matrix, we require total 3 memory elements, 1, 2 and 3. Now, let us see for the observer canonical form realization. Again, let me write down my generator matrix. This is 1 0 0 1, 1 plus D square, 1 plus D. So, we said one set of rows, one set of shift register for each of the coded bit. For each column there is one set of shift register. What is the maximum delay element here? 0. So, you can see directly. What about this? Again, their maximum degree of D is basically 0. So, there is no shift register. And here for the third line, D is 2, so we took 2D. So what is the final output then? First one is first coded bit is just U1 of D, that is what it is. Second coded bit is U2 of D, let's write this, and third coded bit is 1 plus D square of U1 of D. So what is U1 of D? U1 of D is this one. What is D times U1 of D? That is this term. And what is D square U1 of D? That is this term. Fine. Plus 1 plus D times U2 of D. So then what we have is U2 of D is this and D times U2 of D is this. So this is our observer canonical form realization for this convolutional encoder with this generator matrix. And note, we only required 2, 1, 2. We required only 2 memory elements. So same encoder, here we require 2 memory elements. For the controller canonical form realization, we required 3 memory elements. So that brings us to this notion of minimal encoder. We saw the same convolutional encoder with same generator matrix can be realized using 2 different ways, one that resulted in 3 memory elements, other that resulted in 2 memory elements. So we say a generator matrix is minimal if its number of states is minimal over all possible equivalent generator matrix. And among the minimal encoder matrix, a minimal encoder is basically a realization of a minimal encoding matrix which will result in minimum number of memory elements used to represent that particular convolutional encoder. So we define a minimal encoder as the minimal realization of a minimal encoding matrix. So the minimal encoder should result in minimum number of memory elements used to represent that particular convolutional encoder. And for the example that we have considered this, in this case you can see from the generator matrix the maximum degree of D is 2. So we at least need 2 memory elements to represent it, and you can see the observer canonical form realization in this particular example will result in minimal encoder for this convolutional encoder. So this realization will result in minimal encoder realization for this convolutional encoder. Thank you.